Here's where we ended, or close to it, on Friday. So let's just can you name this? Y'all need to make flashcards. This is acetophenone, right? What would be another common name? Phenyl methyl ketone. All right, thus far in this class, how many reactions could you do to this and how many different products could you get? Sodium borohydride, I think there's a little more to it. Like some protonation, what would be the product? What did we learn on Friday? Did you watch the videos while you're sick? Come on, why do I go to all this work? Well, there's now 3 of you that, for whatever reasons, can't come to class. So I'm really thankful that you're all 6 of you are here. Do you need some hints? Do you need to call a friend or something? How about this? And let me put this acid catalyzed hydration. So what do we call this? Just a generic general term. We call it the hydrate, right? This is acid catalyzed hydration. All right, carbonyl carbons react with, what do you call this thing? Yeah, Grignard. And I wrote the Grignard because it was easier to come up with than a Gilman reagent. What's a Gilman reagent? An alky cuprate. They all kind of work about the same here. So this thing's gonna slam into there. And we can just kind of do a little mechanism to help us out. I'm gonna just draw that methyl group down because I might make sure 3-carbon chain, got my 3-carbon chain. So we made a tertiary alcohol. Can we think of any other reactions from this carbonyl chapter? Ketones and aldehydes. So there's our hydrate. We just looked at acid catalyzed with my example problems. Cyanohydrin. We saw another hydrin a while back when we did something like this. And it was an anti-dil. And I believe this would be called a chlorohydrin. So a little similar naming. So potassium cyanide or sodium cyanide. Should know this from your list of nucleophiles. I believe it's a fairly strong nucleophile. The mechanism is a base catalyzed nucleophilic addition attacked by the cyanide ion, followed by protonation of the intermediate. This looks dangerous. This looks like hydrogen cyanide gas. There it is, highly toxic. So this will probably be the heart of today's discussion. More type of addition reactions to carbonyl carbon. So here's a primary amine. Here is a ketone or aldehyde under the presence of acid. You imagine the lone pair getting protonated makes this nice and positive. So this thing can slam in there and So this might be kind of an intermediate. So here's an amine. It's called a Schiff base. It's a base because it's got a lone pair of electrons there. And you can see it's lost water. So it might be called a condensation reaction. And it says ammonia, or a primary amine, we got a primary amine here, reacts with a ketone or aldehyde to form an imine. So if we had ammonia, we'd have a hydrogen here. Call that an amine. Amines are nitrogen analog of ketones. So instead of an oxygen, you got nitrogen. That's what the nitrogen analog means, of ketones and aldehydes. With instead of carbonyl, we have carbon double bonded to nitrogen. Optimum pH is around 4.5, so it's got to be acidic, and this occurs. What is the mechanism? All right, I already alluded to all our carbonyl carbon chemistry that's acid catalyzed begins with protonation of the oxygen, makes the carbonyl carbon more susceptible, makes an electrophile. This thing wants a nucleophile. Slams in there. Water can pull off a hydrogen because this nitrogen has 3 bonds. Here it has 4, has that formal charge of +1. So here's our carbonyl amine. All right, so here's acid catalyzed it. Kind of got our acid back. Put the acid back on oxygen. Now we have a good leaving group. Water can leave. That gives us a carbocation. Stabilized by delocalization of the charge there with those 2 resonance structures. And we can imagine this oxygen, that water, in case we were real anhydrous before. I guess it doesn't matter, there's water. Pull off that, and so here is our amine. Acid catalyzed dehydration. The amine formation is one of the important mechanisms in this chapter. It's more easily remembered as consisting of acid catalyzed nucleophilic addition to carbonyl carbon, and then acid catalyzed dehydration as with an alcohol. I don't know if the mechanism is important as just knowing some of these names, an amine, an oxime, mainly this top half, but it's pretty general. And so I pointed out we got water, so we can call this a condensation, an addition reaction to carbonyl carbon, and we call it condensation reactions because we get water. Be sure and use a coaster when you do this reaction, just kidding. So if Z is a hydrogen, then we just got an ammonia and we get this amine. If we have an alkyl group, a primary amine, we still get this thing we call it an amine. This one we can give it a special name, we can call it a Schiff base. Now if we have an OH here, we have hydroxylamine, that would be the name of the chemical, and we get what's known as an oxime. This week in lab, it's coming right up on me, we're going to use hydrazine. You're going to make luminol, a compound that will cumulesce, give off light. The most exciting lab of the semester. I've got to pump myself up for it, so I'll want to prep it this afternoon. And this is similar to hydrazine, phenylhydrazine, and then something similar. So all these different groups. Most important thing is just to take this first nitrogen and stick it, just erase oxygen and draw it in, and you will have your product. So we talked about the hydrate. So alcohols, kind of similar to water. If I had a hydrogen here, this was 2 hydrogens, we'd have the hydrate. Now here we have this thing called an acetyl And so aldehydes or ketones, they can be hydrated with water, or they can be spiked with alcohol. And we can call these things we can call this an acetyl, we can call this a ketol. The main thing is that you see carbonyl, carbon, and like splitting the oxygen and getting the acetyl or the ketol, and it should look just like the hydrate. So if we know the hydrate chemistry, we should know the acetyl chemistry. The only thing that's a little bit different here is we get this thing known as a hemiacetal. What does the word hemi mean? Yeah, it means half. If I pull out your globe, and we all live in the north what? Hemisphere. Half. Yeah, so fancy word mean half. So here's our ketone, here's an acid, gets protonated, makes this thing susceptible to nucleophilic addition. Here's methanol, it's going to be our alcohol, that slams in there. All right, and then our methanol oxygen now has 3 bonds. Alcohol can act as a base, pull that proton off. So we've kind of like regenerated our acid catalyst there. And this is called the hemiacetal. Looks half hydrate, half acetal. We'll call it a hemiacetal. These things must be acid catalyzed. Adding a proton to carbonyl carbon makes it more reactive with a weak nucleophile. Remember your list of nucleophilicity, strong and weak nucleophiles. So here's our hemiacetal. We'll protonate the OH, makes a good leaving group. Now we're back almost to where we started. And so the second alcohol can come in right here, attacked by methanol, an oxygen with 3 bonds. And so we've regenerated our acid catalyst, and here's our acetal. So we call these things condensations. So think Le Chatelier's principle. If we add some water and we're still acidic and we add an excess, the opposite of condensation is hydrolysis. Acetyls can be hydrolyzed by the addition of dilute acid. Mainly the excess of water drives this thing back this way. So we can get our ketone and aldehyde back. So here's benzaldehyde, here's ethylene glycol. Notice it's like methanol there and methanol there, 2 methanols stuck together. And so look at this interesting acetal. Here's our carbonyl carbon. Think putting 2 alcohols on there. There we stuck our 2 alcohols on there. And this has a benzaldehyde, ethylene, acetal. So the addition of diol produces a cyclic acetal. There's a cyclic acetal. And this reaction is somewhat reversible. We see the equilibrium areas, so with Le Chatelier's principle, we can make the acetal, and then we can go back to our aldehyde if need be. It says this reaction is used in synthesis to protect carbonyls from reaction. We call this a protecting group. Acetals as protecting groups. So here's a ketone, here's an aldehyde, and it's easier to form an acetal on the ketone. Excuse me, that was a Freudian slip. On the aldehyde than it is the ketone. So here's our ethylene glycol, acid catalyzed. Now if we want to do some chemistry on the ketone, we can do this. It says hydrolyzed easily in acid, stable in base. So we could do a Grignard reaction on this now. We could react it with an amine. So this is just a experimentally determined thing, and that's kind of nice. We can have some selectivity here. Formation of an acetal or hemiacetal does not alter the oxidation state of the carbonyl carbon. In an acetyl or hemiacetal, the carbonyl carbon atom is the one with 2 bonds to oxygen. So you saw this reagent right with my example problem to review some of the chemistry. Sodium borohydride reduces ketones and aldehydes to either primary or secondary alcohols. And then the acid here removes the protecting group. The acetyl will not react with the sodium borohydrate, so only the ketone will get reduced. Hydrolysis conditions will protonate the alcohol and remove the acetal to restore the aldehyde. Aldehydes are easily oxidized to carboxylic acids. So in general, aldehyde oxidizing agent goes right to the carboxylic acid. And so here's our chromate, goes right to the carboxylic acid. Silver oxide in THF oxidizes this to the carboxylic acid. So the tolerance test, you use to test for an aldehyde. I typically think about it with reducing sugars. So it involves adding a solution of silver ammonia complex, that's the Tollen reagent, to the unknown compound. If an aldehyde is present, its oxidation produces silver ion to metallic silver, and when you do it in a flask, it's like you make a mirror out of the flask. So sodium borohydride can reduce ketones to secondary alcohols, aldehydes to primary alcohols. You already know this from the alcohol chapter where we went over these reagents. This thing can also reduce esters. Lithium aluminum hydride is a powerful reducing agent, so it can also reduce carboxylic acids and their derivatives, like esters. So catalytic hydrogenation can reduce the carbonyl carbon, but it will also reduce any double bonds or triple bonds present in the molecule. So here's our cyclohexane carbaldehyde, sodium borohydride. So this is just solvent to run the reaction in. You know, this is a solid, and you got to dissolve it up. So here we reduced our aldehyde to a primary alcohol, cyclohexyl methanol, butane 2-one. Here's 2-butanol, or butane 2-ol. And so this could not reduce esters, carboxylic acids, acid chlorides, or amides. So aldehyde or ketone reduced to corresponding primary alcohol or secondary alcohol. Guess lithium aluminum hydride is difficult to handle. That just makes it more exciting to use. So here's the catalytic hydrogenation, and it's going to reduce this double bond and this. Here they show it reducing the double bond first. You can't stop it halfway with stoichiometry. That's why you'd use one of those other reagents if you still wanted your double bond at the end. Widely used in industry. They call this rainy nickel, finely divided nickel powder saturated with hydrogen gas. Reduces the alkene first and then the carbonyl carbon. Deoxygenation of ketones and aldehydes. So we can just remove the carbonyl carbon. It takes us 2 electrons to get to there, 4 electrons to get to here. How would you know 4 electrons or 2 electrons? You go back to the electrochemistry chapter in Chem 2, and you use the method of half reactions. and poof, out will pop the number of electrons you need. This isn't that class, so I won't make you have to know that. So we looked at the Clemmensen reduction in the previous chapter with the phenyl Kraft acylation when you have a phenyl group and you stick on this 3-carbon chain, and the Clemmensen reduction was amalgamated zinc, drip in HCl, and this reduction occurs. Here's an aldehyde. It's all the way reduced down. So this is all done under acid conditions. What if we have a compound that is sensitive to acid and we can't have it around any acid? We have this thing called the Wolff Kishner reduction. Involves hydrazine. So here's a ketone. We add the hydrazine. It makes a hydrazone. So remember that slide that had all those additions for the amine, the oxime. I said it's just pretty general. The nitrogen goes where the oxygen was. There it is. So we use basic conditions. This diethylene glycol is just you might, we're going to actually use something like this tomorrow. I use brake fluid because I tried to order some expensive material like this and it never showed up. And so I used, there's a YouTuber called The Rage Chemist. We use his recipe to make luminol. All right, enough of that. But you couldn't use an aqueous solution because look at the temperature, 175 degrees. So this diethylene glycol has a much higher boiling point than that. So you can heat that up to that temperature and we've reduced the carbonyl carbon. Forms a hydrazone, then heat with strong base like potassium hydroxide or that bulky base, potassium tetrabutoxide. High boiling solvent like ethylene glycol, diethylene glycol, or dimethyl sulfoxide. A molecule of nitrogen is lost in the last step of the reduction.